I pushed the wrong button, and I got a diet now too. So I'm not going to be probably as good as whatever good means, but I'm not going to be at the same level. I'll be at a lower level because I'm not having caffeine. It's not caffeine. I think it's the sugar. I like the sugar. I went to an ice cream place, and I think they said a fancy word which meant something less fattening, and I looked at them and I said, does that mean something somewhat dietary, a diet type of ice cream? And they said, yes. And I said, no ma'am, I'm not looking for a diet ice cream. I'm here for the full, I like the full thing. It's time for us to get started. This is our 26th lecture. I want to start today, before we get into content, I want to start today by reminding people something. I think it's a reminder, but it might not be. There is a celebration of scholarship conference upcoming on Wednesday and Thursday of this week, and many of your classmates are participating here. I will name just a few, and I hope they're okay with me naming them. Megan is presenting, Audra is presenting, Chuck is presenting, Mark Teeters, who's in this class, although taking it kind of remotely through videos, is also presenting. There might be more, but those are some of the people that I remember seeing their names. There might be others. I don't know. Did I miss somebody? Okay, and so other people have already presented in it. Jonathan Clevenger last year presented it. So it's a nice thing to do, and it's not a necessary thing to do. I think Chuck presented last year and won an award, a Dean's Award, did you not? Good for you, Chuck.
Thank you.
So those are nice things. So I just want to mention that, so you can go and attend your fellow students' talks and see what they've been working on if you'd like. And you don't have to, it's open to go. It's not something bad. It's something good to do if you want. If you got something else to do, that's okay too. One of the things that's a personal preference for me, Melissa, is I don't think we should force students or force anybody to do so. This is open. You should go if you want to go. If you got something else to do, understood. That's back. All right, that's, having said that, next thing I want to tell you is that homework number 4 is due on Friday. And I wanted to do at least one problem, mimicking something that's there in the homework. So I'd like to show that a particular sequence, I want to do something like 2b. I want to show a particular sequence is either increasing or decreasing. Okay. So here, let me do an example. Let's say I had this. Let's say I wanted to show that, I don't know, let's say n squared minus 4 over n plus 1. Let's make it n plus 3. I think it's increasing. I don't know that it is. Okay, so I'm going to put that in quotes, put the parentheses, the question mark in parentheses, because I didn't try this ahead of time. So I want to see, okay? So let's see. Let's look at some of the terms. When n is 1, I get minus 3 over 4. When n is 2, I get, I think, 0. When n is 3, I get 5 over, so that'd be 3, it'd be 5, 9 minus 4 is 5. Remember, n is 3, so I get 5 over 6. When n is 4, I get, I think, 16 minus 4, that's 12 over 7. When n is 5, I get 21 over 8. I think those are getting bigger. That's what it looks like to me. That's what it looks like. Okay? Okay, so they look like they're getting bigger. And so here's what I want to do. Let's see if we can prove it. So we want to show, here's what I think, this sequence is increasing. Just from looking at the term. But I don't know. So I want to see if I can prove it.
So this is like problem 2B from the homework. And so to prove it, what do I have to do? To show a sequence is increasing, we must show, well, the definition is that x of n is less than or equal to x of n plus 1. That's what we need to show a sequence x of n is increasing. So here, we must show that, well, what would be the x of n term? It would be n squared minus 4 over n plus 3 is less than or equal to, it would be n plus 1 squared minus 4 over n plus 1 plus 3. So that's the x of n term, that's the x of n plus 1 term. That's what we must show. I don't have that. Okay? That's what I got to show. And so we must show that here, n squared minus 4 over n plus 3 is less than or equal to, this top would be n squared plus 2n, then it would be minus 2. I want to show that over n plus 4, we want to show that that's the case. Okay, I don't know that it's the case, but I believe it's probably the case. I think I did that correctly. I didn't. It's n squared plus 2n plus 1 minus 4, so it should be minus 3. That is, we must show, thank you, Dalvin, that n minus 2 times n plus 2 over n plus 3 is less than or equal to, this factors, it's n plus 3 times n minus 1 over n plus 4. I want to show that. So I'm kind of narrowing it down what it is I need to do, okay? To try to find something that I know is true, that I can do. You know, this is same as showing this, same as showing this. If I could do this, I'd have it. I'm trying to get down to something I can do, that I know to be true. And I want to thank Chuck very much for bringing this to my attention to do an example of it. Thank you. So here, if I cross multiply, this will be the same as we must show, and we'll be multiplying the cross multiplication for all in by something positive. So here, I'd have, looks like n, I'm going to multiply everything by n plus 3 times n plus 4. That's what I should say. We must show that n, right up here, n minus 2 times n plus 2 times, I think, n plus 4, if you will, is less than or equal to, here I'm going to say n plus 3 times n plus 3 times n minus 1. That's what I got to show. Is that okay with everybody? I think that's pretty much it.
So we can expand it out.
Yeah, we sure can. So maybe we want to expand it out and see what this is. Well, this guy is going to be n squared minus 4 times, here it's n plus 4. So these, or this, is less than, here this is n squared plus 6n plus 9. And then this is times n minus 1. That's right. And maybe I wouldn't have to do this, but I think that in this case, I probably do have to do this. Maybe I didn't even multiply this out the best way possible. Let us leave this instead at n minus 2. And what if I multiply these two guys out instead? What would I get? I'd get n squared plus, well, it's 8n, isn't it? Plus 8. Isn't that right? Well, anyway, that didn't seem to help very much. It didn't matter. I was trying to compare things.
I think it should be plus 6.
It sure should be. Now that does help everything. Yeah, so let's multiply those two together instead. It should be 16. Sure should. And the reason that I said that I made a mistake is that when I compare things, n minus 2, how does it compare to n minus 1? Yeah, the one on the left is less. How does n squared plus 6n plus 8 compare to n squared plus 6n plus 9? Smaller. And so here I'm going to multiply two smaller numbers. And so here's what I would do. Okay, I'd start here. Note, I think I've seen the spot from which I can get started. Okay. Note, n minus 2 is less than or equal to n minus 1. And that's true for all n of the natural number. So that's where I'm going to start. I'm ready to prove. Okay? That's where I'm going to start. Thus, n minus 2 times n squared plus 6n plus 8 is less than or equal to n minus 1 times the same quantity. Now that's what I want to write. I've written what I want to. And the reason that that's true is that I have this inequality that I'm starting from. I'm multiplying both sides of this inequality by a positive number. Is that okay? And so, when I multiply it by a positive number, then I'm going to keep the inequality. Is that okay? Okay, on this side, we have n minus 2 times, I think this was n plus 2 times n plus 4. Is less than or equal to n minus 1. Now, what I'm going to do is increase this. So I'm going to increase this by a non-negative quantity. So I'm going to write down n squared plus 6n plus 8 plus, for n being greater than or equal to 1, n minus 1. So all I'm doing is adding a non-negative quantity here. When I say adding a non-negative quantity, for all n minus 1 is greater than or equal to 0. I'm doing that because I'm trying to get to here. Okay? And so if I factor out n minus 1 from this side, I'm going to have this plus 1. And that's going to give me exactly this. And the problem I'm asking you to do, I don't think it's as complicated as this one I just made up on the spot. Not as hard, okay? But this is kind of the idea. You work down the original problem for comparing x to the n and x to the n plus 1, and to get down to something you know is true and work from there, okay? So, what I have here is n minus 2 times n plus 2 times n plus 4 is less than or equal to, here's what I have, n minus 1 times n squared plus 6n plus 8. No, not plus 8, but plus 9. And so this says n minus 2 times n plus 2. Isn't that n squared minus 4 times n plus 4? Is less than, I think it's n minus 1 times in this n plus 3 times n plus 3. Isn't that right? Okay. Now I've forgotten the original problem that we had, but I think it had n squared minus 4, and then I'm going to say that's less than, I'm going to divide everything by n plus 4. So n minus 1 times n plus 3 times n plus 3 all over n plus 4. Now I'm going to divide everything by n plus 3. So I have n squared minus 4 divided by n plus 3 is less than or equal to, I made a mistake, less than or equal to. Here I have n minus 1. I'm dividing everything by n plus 3. N plus 3, that guy lives. This n plus 3 is going to be canceled out and n plus 4. So what I get is n squared minus 4 over n plus 3 is less than or equal to, when I multiply this out, I get n squared This is going to be, I think, plus 2n minus 3 over n plus 4. Isn't that right? Isn't that what I have?
Yeah, I think so.
And then what I'm going to do is I'm going to say, so n squared minus 4 over n plus 3 is less than, I'm going to rewrite this, I think it's n plus 1 to b squared. So that's n squared plus 2n plus 1 minus 4 over, this is n plus 1 plus 3. That's what's in the bottom. N plus 1 plus 3 is n plus 4. I'm just working exactly backwards from what I had. And so this says x of n is less than or equal to x of n plus 1. So that tells me that x of n was an increasing sequence. So in doing this problem, we kind of need to know from what point to start. And so where we find the start is kind of by assuming what we're thinking is true and running through saying what it's equivalent to. And we ended up getting to, really I'm going to move the camera. We ended up getting to the spot that I want to emphasize is this one. When I got to this spot, I knew that I could say, hey, these two guys have an inequality comparison that I start with from here, and then I just multiply by things that are bigger. And from there, I can get the result I want. And it's kind of working backwards. Is that okay with everybody?
I got a little lost when you added n minus 1 to our inequality. Can you explain that one more time?
Yes. So here, you're talking about this line right here. Okay. So if you don't, here's really what I'm doing. Thank you very much, Audra, for asking. Here's what I'm doing. I want you to notice that n minus 1 times n squared plus 6n plus 8 is some number. It's something. And that's what we had in the line above, the right-hand side. So here's what I'm going to do. I'm going to say that's less than or equal to the exact same thing plus any non-negative number. So as long as I write down something here that's non-negative, I'm good. So if you take some quantity and you add something positive to it, it just got bigger. If you add 0 to it, it stayed the same. I claim that n minus 1 for all n values is something that is non-negative. It's either 0 or it is bigger than 0, so it's positive. So here's what I'm doing. I'm taking this guy and I'm either adding something positive, so the result would be bigger, or I'm taking this guy and adding 0 to it, which means it would stay the same. And that's how I get that inequality. So I'm just comparing previously the right-hand side of the inequality to now a new right-hand side of the inequality that is bigger. Or bigger than or equal to it. Is that okay what I said? Yeah. So as an example, I think the example again, Brad, is something that's tougher than what I'm asking you to do in the homework. Okay, making something, this was something tougher. But again, with this, the process is the same. You get to some point, you reduce down what you want, and you get down to some point that you know to be true. And you say, from that, I work in reverse order what I did. Chuck, is okay? Okay, having said that, I now will open up the floor to any questions you might have from the homework or anything else that we covered. Anybody want to ask anything? Yes, sir, Brad.
Not really a question about the material, but are you going to post or have you posted the lecture from Friday? Because I have not seen it as of an hour ago.
The answer is that I posted it about 12:58. So the answer was not until 12:58, but it's now available online. I hope it's okay to not watch it at this point. But yes, I'm sorry about that.
That's perfectly fine.
That's right. And thank you for reminding me to do it. Sometimes I need that. Anybody else with a question or comment? Okay. Well, if you have questions as you're doing the homework, I think I said when I passed out the homework, I think problem 4 and 5 are a little bit sneaky. And so if you're trying to work on them and say, well, I don't know what to do, that's normal. And so if I can give you a small hint that might kind of nudge your way to getting the solution, please come by. Let me give you a hint. I have 2 hints. I have a hint to give for each problem that was valuable to me. Please let me know. Okay. All right. Well, I want to remind us where we were. So let's recall we were working on limits of functions. And here's the main definition. Before I write this main definition, Audrey, on the problem that I asked you in the homework, I don't think you have to make this type of move where you have to add something more to it. So the definition, the limit, we say let A be a subset of R, F goes from A to R, and to be talking about limits of functions, C needs to be a, that's right, sure is, that's right, plus of A. Then, in terms of notation, the limit as x goes to A, x goes to C, I'm sorry, C. X goes to C of f of x equals L if for each epsilon greater than 0, there exists a delta greater than 0, such that, excuse me, for all x in A with, don't forget it has a 0 here, 0 less than x minus C less than epsilon, less than delta, then the distance between the output values, f of x and L, will be less than epsilon. So that's its definition. Right? We had done at least one example that was easy to do. It was a linear example. And the reason that it's easy to do is that here's what you get to control, everybody. You get to pick the delta. Okay? Somebody gives you an epsilon. Maybe you don't even know what it is. They're just saying, here it is, it's positive. And you've got to find the delta. So you get to control how close x is to C. That's what you get to control. And by controlling that, you're going to make the output values be really close to L. Does that make sense? Output values for the function. So when you have a linear function, what you do is you rewrite what you want to have happen, the output values being really close to L. You get to manipulate every time it'll happen into something you can control. That's what happens every time. Let me show you the easiest one of these. We did a linear example before. Let me show you the easiest linear function. Here's a fact. The limit as x goes to C of some constant function, b, is equal to b. Pictorially, here's what we're thinking. If you say, hey, as I get really close to C, what are the output values getting really close to, if anything? And the answer is, the output values are not only getting close to it, they are B, all the time, etc. So everything's really close to B within epsilon units. Here's my epsilon here. And the question is, how close do you have to be to C? Well, the answer is, it doesn't matter how close you are to C. Any value for delta will work. Is that okay? And so let us see that in the proof. So here's the proof. We let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all x that are real numbers, that's the domain of this constant function, with 0 less than x minus or c, whatever it is, being less than delta, then absolute value of f of x minus L will be less than epsilon. That's what generically the definition is. But now I want to work with the specifics for our particular function, f of x equal to b and L equal to b. That is, this is what I want to force to have happen. And this is the way that I get to make it happen. By controlling how close x is to c. We want, so let me say what we want. We want f of x. What's f of x? B minus, what's L? So here's f of x. What's L? We want that to be less than epsilon. We want, well, what's b minus b? An absolute value of 0? We want 0 to be less than epsilon. Well, epsilon is greater than 0. So any delta bigger than 0 will work. Okay? Let's give a specific delta. Let's let delta be equal to 1. It didn't matter what positive number I picked. Then, for all x element, for all x element of R with 0 less than x minus c less than delta. Before I go any further, I'm saying this is 1. You go 1 unit to the left of c, so this is going to be c minus 1, this is c plus 1. Anytime you're within this region and you look at the output values, are the output values within epsilon units of b? Yeah, they're all in this band of being epsilon units of b because they're all at b itself. Let me finish this up over here in terms of the formal writing. So for all x's in R with 0 less than x minus c is less than delta, then f of x, which is just b, f of x inside absolute values, minus L, which is just b, will be less than epsilon. If you want, you could just say b minus b. So that means that the limit as x goes to c of b equals to b. And that's the proof. Well, that was easy. Let me show you something not easy. Linear are easy. Quadratics was tougher, is tougher. But I'm going to do it by the definition. Okay? And we're not going to do all function types in the world. We're going to do quadratic. Okay. So here I'll fact. Write down this fact, prove this fact. The limit as x goes to c of x squared equals to c squared.
We take delta equal to 1, but we don't necessarily implement it into our...
No, it didn't matter what delta I picked. I could have picked delta equal to 79.
Okay.
It didn't matter. The proof doesn't depend on delta. Any delta will work. Okay? But I happen to pick delta equal to 1. But your observation is exactly right. Your observation was we didn't use delta equal to 1. But I'm supposed to give a specific delta.
Okay.
So I did. I said 1. But I didn't have to pick 1. I could have picked anything. Any positive number. I could have picked a half. Anything. I want to show this is true. Well, Chuck, let me start making excuses. Last time I did this problem was a year ago.
So my excuse was I was so lazy that I didn't prepare. Let's see how it goes. It's harder. Yeah, much harder.
Okay, so here's what happens. We let epsilon be greater than 0 be given. We need, what do I need? Oh man, I need a K. No, I don't need a K. A K is what we need when we add sequences. We need a delta. I need a delta. It's like an airplane. And delta greater than 0, such that for all x in the domain, here it's all, with 0 being less than x minus c being less than delta, then the absolute value of x squared minus c squared will be less than epsilon. So this is what I want. I rewrote it this time without an intermediate step of just using the definition. I went ahead and applied the definition to our particular situation. And this is what I want to have happen, and I'm hopeful I can get that by controlling the input values. Okay? And I can, but it isn't as direct as what it is for linear. Not as direct. So here, we want x squared minus c to be less than epsilon. That's what I want. But that's the same thing as 1. So we want the absolute value of x minus c times x plus c to be less than epsilon. That's what I want. Okay. Now look, what I get to control, well, wait a second. I'm going to write down one more statement. It's equivalent. So what we want, so the equivalent statement I'm going to write is that we want the absolute value of the quantity x minus c times x plus c to be less than epsilon. But the absolute value of the product is the product of the absolute value. So we want x minus c times x plus c to be less than epsilon. Here is the idea. The idea is I get to control how small this is. I want to make this multiplication be very small. Is that okay? So I get to control how close x is to c. And I'm hopeful by making that part small, I can make this whole product be small. So what I have to do is by controlling this guy, making it very small, I'm hopeful that by making x be very close to c, it makes x not be that far away from minus c. That's one way of looking at it. It controls this guy too. That makes sense. If you say x minus c inside absolute values is less than some number, isn't that going to force the absolute value of x plus c not to be too big? Well, how big? So here's what we do. We kind of, it's very innovative. Somebody says, well, look, you're going to get to make this be as small as you want. Okay? So what if you just say, let's let it be less than 1? For x values, with x minus c being less than 1, we have, so I'm going to write down a bunch of steps, and they're all pertaining to this situation. Okay? I'm not going to put periods. We all talk about the same situation. For x values such that their distance away from c is less than 1. 1 unit to the left, well then 1 unit to the left, 1 unit to the right side. Then, one thing I can do is rewrite this as a statement without absolute values. How can I rewrite it as a statement without absolute values? That's that famous fact we learned and when we're talking about properties of real numbers involving absolute values. What can I rewrite it as? What's the first thing I'm going to write? That's exactly right. Less than x minus c is less than 1. What the heck do I want? I want to control the absolute value of x plus c. So in the middle, I want x plus c. Is that okay? And on the right and left-hand sides, I want two numbers. One's positive, and I want the negative on the left-hand. Or left-hand side. Yeah, that's your left. Is that okay? That's what I want. So that I can rewrite this compound inequality as a inequality involving absolute values. And what do I want in the middle? X plus c. I want to talk about this guy. Okay? I want to control this guy. Okay? By controlling this guy. All right, well, How do I get x plus c in the middle?
Add 2c.
Minus 1 plus 2c. That's right, John. Is less than x. When I add 2c here, I'm just getting plus c. 1 plus 2c. Remember, what I want is I want a positive number here, and it's negative over here. I don't even know that 1 plus 2c is positive. Is that okay with everybody? So what I'm going to do is I'm going to stick in something more negative than 2c, something less than 2c, and something bigger than or equal to 2c, and that is, I'm going to say this is minus 1 minus 2 times absolute values. So 2c is less than, 2c is bigger than minus the absolute value of 2c. Remember, any number is sandwiched in between its negative absolute value and its absolute value. Any number is sandwiched in between those. It's less than or equal to its absolute value, yet it's bigger than or equal to minus its absolute value. Okay. So that, x plus c, and again I'm going to do the same thing here. I'm going to write down 1 plus 2 times the absolute value of c. So when the absolute value of x minus c is less than 1, then the absolute value of x plus c in absolute value is going to be less than 1 plus 2 times the absolute value of c. Is that okay with everybody? Okay. That's what I need to say. Okay, I need a second. So I need to pick the delta. Delta is going to be a minimum here. Oh. All right, I'm going to try this. I'm going to say let delta equal to the minimum of 1 and epsilon over 1 plus 2 times absolute base. Why did I pick this? Well, I knew when I have x minus c inside absolute values being less than 1, then the other part that's involved in what we want, absolute value of x plus c, is going to be less than this quantity. Is that okay? Less than this quantity. Okay. And so, with it being less than that quantity, I could substitute this part right here, this bottom, in for x plus c. Okay. And then maybe use the fact that x minus c inside absolute values is less than both of these, less than both of these, to substitute that in for x minus c inside absolute values to get the result I want. I'm ready. Let's check it out. Okay. Then, for all x in R, with 0 less than x minus c is less than delta. I want to stop for a second. We're going to go to this proof. But I want to make an observation. In our work previously, when we were working with sequences and we wanted to have more than one thing happening, with the sequences, what we did was we went to the maximum. We had to get beyond both things that were occurring, or all things that were occurring, to get them all. For limits, you're saying, as long as you're close enough to C, good things will happen. Whatever the things you want will happen, okay? So if you have several things happening that says if you're close enough to C, what you've got to do is to make sure that you're in the minimum distance, the closest distance that you require of C. Is that okay? So instead of taking the maximums, when we talk about limits, we're going to be taking the minimums, okay? That's why I did this above, okay? Okay, now look. if x minus c, and inside absolute values, is less than delta, what is delta? Delta is either 1 or it's this guy. If it's this guy right here, then it's less than 1. Is that okay? Because this is the minimum. If it's this guy, then this is still less than 1, if delta is equal to 1. So no matter what, x minus c inside absolute values is less than 1. Is that okay? Then, the absolute value of x squared minus c squared. Remember, that's the guy we want to show is less than epsilon. That is the thing we want to show is less than epsilon. That is equal to the absolute value of x minus c times the absolute value of x plus c. And we know this part being less than delta means that this part, x minus c inside absolute values, is less than 1. And when this guy is less than 1, this guy right here was less than 1 plus 2 times absolute value of c. It's on the other board. So I'm going to replace this by something bigger. So the whole thing's going to get bigger because I'm going to replace it by something bigger. So this is less than or equal to absolute value of x minus c. I'm not touching that guy. But what I'm replacing this guy with is something bigger. What's something bigger? Something bigger is 1 plus 2 times the absolute value of c. But wait, x minus c is less than delta. That means I know it's less than each one of these guys. Is that okay? It's less than the minimum, it's less than both of these guys. So definitely something bigger than x minus c is I'm going to replace this with this guy, which is epsilon over 1 plus 2 times the absolute value of c. And then times this guy. So look, from this step to this step, all I did was replace this with something bigger. Okay? I replaced this with something bigger. Now, from this step to this step, I'm replacing this guy with something bigger. So it gets bigger. But wait a minute, when I multiply these together, what do I get? Epsilon. So, for all x in R, with 0 less than x minus c is less than delta, absolute value of x squared minus c squared is less than epsilon. What's that say? That says the limit as x goes to c of x squared equals to c squared. And that's the proof. Go ahead. Much harder to say. Why did we pick this to be the minimum? Well, it works, but it's much harder to see that. Yes, sir, John.
Do we have less than or equal when we should have less than?
Here, I should have less than. That's correct. Yes, you're right. It should be less than. So that's equal to. And we need that to make this final point. You're right. Yeah, that's a good comment. Yeah. That's beautiful. That's equal to. Okay. Wonderful. Okay. Yes, sir.
I got kind of lost with the second term of that statement there for the minimum.
I'm pointing right here. Am I in the right spot? Up. Here? Yes. Okay. Look, I can let delta be any positive thing. Okay? So 1 is a positive number. Epsilon is positive. 1 plus 2 times absolute value c is positive. Positive divided by positive is positive. So I'm saying let delta be the minimum of these two things. So either delta is this guy or it's this guy. So delta is positive. Why pick that? A little tougher to see. But I'm saying to pick that because it will work. Okay. Why? We did a lot of work when we know that the absolute value of x minus c is less than 1. So that's why I want that involved. But when we work with x minus c being less than 1, it forced the absolute value of x plus c to be less than this denominator. Is that okay? And so that's why I'm replacing this. This is bigger than this when x minus c is less than 1. Which it is if we're saying that x minus c is less than delta. Okay? And so once I get here, I also want this to cancel out with this guy. And so something bigger than that is this. Not as easy as working with a linear function, okay? I couldn't get what I want out of what I had with the linear function, what I could control in this quadratic case. I could relate it, Here's what I get to control, and it's related in what I want. But it isn't just all of what I want. Totally get to control it directly. But I do kind of indirectly get to control it because I get some control on this guy. I live in X minus C less than. Okay. Well, the next thing I want to do is something similar that we had for limits of sequences. That's the following fact. Here's the theorem. It says limits. I'll write it that way. If the limit as x goes to c of f of x exists, it may not exist, then that limit is unique. You know, we had an analogous statement with sequences, and that analogous statement was the following. What we had said was there can be at most one limit. Well, that's the same thing we're saying here. There can be at most one limit for functions, okay? We're going to do that next. And the proof is very similar to the proof for the sequences, okay? What was that proof? It was a proof by contradiction. That's right, Joe. That's right, Joe. So here's the proof. Let the limit as x goes to c of f of x exists. Suppose, so I should have written by contradiction. Suppose that limit is not unique. That is, suppose the limit as x goes to c of f of x equals to L sub 1, and the limit as x goes to c of f of x equals to L sub 2, with L sub 1 being different than L sub 2. They're not the same limits. Well, that's going to lead to a contradiction.
We need to say without loss of generality.
I am going to write that next. Almost next.
Okay.
That's right. And without loss of generality, what am I going to write, John?
That we can assume one is bigger than the other.
Yes, sir. That's exactly right. And that's what we did in that other proof. Okay? Before I do that, though, John, we'll give a picture. Look, here's C. Okay? And we're saying, well, look, maybe this is L1 and L2. And they're not the same, one's bigger than the other one. And I'm going to say, like you said, John, I'm going to let L2 be the bigger one, not L1. So look, here's what happens. When I get really close to C, all the output values got to be in here. Got to be within epsilon units of L sub 1. But they also got to be within epsilon units of L sub 2. So they all got to be in here. They can't be, the output values can't be all in here and all in here. As long as I don't allow for any overlap. Is that okay, between these bands? You know, if I pick bands small enough such that there aren't any overlaps between them. You know, if I pick a huge band, then there's going to be overlap between themselves. So what band do I pick? What do I let my epsilon be? What do I get here?
Yep.
What is, okay. Perfect. That's exactly right. As when I was a child, I watched Happy That Piece, and Fonzie would say, exactamundo. Exactamundo. Hey. So here, without loss of generality, say, as John was saying, L2 is greater than L1. So what that tells us is that L2 minus L1 over 2 is going to be greater than 0. And Brad, that's like my epsilon. This is a positive number, right? So that's going to be my epsilon. So here's what I'm going to do. Since the limit as x goes to c of f of x equals to L1, then there exists a delta of 1 such greater than 0. Be careful. Such that we run out of time. For all x element of a, whatever a is,
The domain of the function.
with 0 less than x minus c is less than delta, then the absolute value of f of x minus L1 will be less than L2 minus L1 over 2. Listen, I've run out of time. And so I'm going to stop there. But I'm going to tell you that what is going to be the way the proof's going to go. We're going to work with this just for a few minutes, rewrite it as a statement without absolute values, and get some kind of idea where f of x, not the absolute value of f of x minus L1, just f of x itself. What's it got to be between? Okay? And we'll get it in between here. And then I'll do the same thing, except working with f of x in L1, I'll work with f of x and L2, and I'll say that f of x has to be in here. And it'll be an inequality that contradict each other, okay? Just like what we did with the limits for c. It's the exact same thing. I'm going to finish it up next time. Thank you very much. Don't forget to work on the homework. Thank you.
Wait, we had homework?